Hi, welcome to Algebra 2 Common Core. Today in Lesson 9, we're going to continue with what we worked on in Lesson 8, modeling with quadratic functions. If you don't have your graphing calculator with you, please pause the video and go get your calculator because we're going to be using it throughout today's lesson. Let's start with exercise number 1. A skateboard half-pipe ramp has a shape in the form of a parabola, whose equation is y equals, and you can see the equation there, where x represents the horizontal distance across the 20-foot wide half-pipe, and y represents the ramp's height above the ground in feet. Find the minimum point of the ramp algebraically. Check this answer on your graphing calculator. First of all, when we examine this equation, we notice that the equation has a positive coefficient in front of the x squared. So that tells me that my parabola is going to be facing up like a cup. Therefore, instead of finding the maximum point like we did on the last exercises in the last lesson, we're going to be finding a minimum point because our turning point this time will be on the bottom of our parabola if our parabola opens up. So it's still the same process that we used yesterday, finding the vertex. So anytime I have a parabola and I want to find the turning point, I'm going to start with that equation, x is equal to negative b over 2 times a. So for this one, we're going to negate the coefficient of the x term, so negate the negative 1.2, and divide by 2 times 0.06. Now yes, I typed this into my graphing calculator, and I got as my x value for my vertex, x is equal to 10. Now, since I want to find the whole point, I need to take that 10 and substitute it into my equation. So we're going to find the y coordinate at 10. So again, I'm going to show my work by 0.06 times 10 squared minus 1.2 times 10 plus 7. And again, yes, I'm going to use my graphing calculator to calculate that. One thing you could do is store 10 in your x coordinate and then type your equation in with x in it. And I notice that I actually get a nice clean number here. My answer is 1. So that tells me that the minimum point on this ramp is going to be located at the point 10, 1. Now, what does this mean on my graph? Pause the video for a few minutes, set up an axis like I've done, and then type this equation into your graphing calculator. In our calculator, I'm going to change my window around. So I'm going to say, let's make our x coordinates go from a minimum of 0 to a maximum of 20, because that's the width of my half-pipe ramp. Let's make my y values go from 0 as well, because I want everything above the ground, up to perhaps 10 for my y maximum. So reset your window and type this into your calculator, and then come back and take a look at my graph and see if your graph matches mine. Take a look at our graph. So your graph on your calculator should match what we're drawing on our paper and our notes. So first of all, I've labeled my minimum point at the point 10, 1, and I've specified that it's a minimum point. The other thing I went back to do is to find the y-intercept of this graph, because when I looked at my graph, I wanted to see where the ramp began. So I substituted x equals 0 in for my x value, and I found out that the y-intercept turned out to be 0, 7. So I labeled that as well on my graph in my notes. So we see that this is what our ramp would look like. And again, the important part was that we found the minimum point on our graphing calculator as well as algebraically. Now in exercise number 2, we're going to have to do some work in order to create our quadratic equation. So we see that a farmer has 2,000 yards of fence. He wants to use that fencing to enclose a rectangular field. we want to find out what are the dimensions of the rectangle that encloses the most area. When I see those words most area, that means that I want to find the maximum point on my quadratic equation. So the maximum point on my area equation. So let's see how we're going to approach this. I'm going to start with my variable and say, let's make the length of this field equal my variable x. So let's make the length go this direction. Opposite sides of my rectangular field are congruent to each other, so I'm going to call them both x. Now it's important that I remember that I had 2,000 yards of fencing, because in order to come up with a way of representing the width of my field, I want to be able to use the same variable. So if to begin with I call it w for width, I will know that 2 times the width, so 2 lengths of the width, plus 2 of the lengths has to equal the fencing 2,000. So right now I don't have a way of representing the width, so I'm just going to call it 2w for a minute. And we do know that the length is being called x. Now I want to have a way of representing the width in terms of x, so I'm going to take that x variable and move it over to the other side of the equation by subtraction. So I'll have 2,000 minus 2x. If I then divide both sides of the equation by 2, that's going to give me a way of representing the width of the field. So dividing everything by 2, I'll have 1,000 minus x. So I'm going to use 1,000 minus x to stand for my width. So that's going to be represented right here, both the top and the bottom. Now what this question is really asking us about is the area. So let's recall that area for a rectangle is always equal to length times width. So I'm going to take my area and represent it in terms of the variable x by saying that the length is x and the width is 1,000 minus x. So simplifying this by using the distributive property, I have an equation for the area, 1,000x minus x squared. So this becomes my quadratic equation that I am going to use in order to find the maximum area. You'll notice that this quadratic equation, even though I've written it in a different order, this quadratic equation has a negative in front of my x squared. So that of course tells me that my parabola is going to be facing down. When the parabola faces down, the turning point is going to be a maximum point. So we are just being asked to find the turning point. So to find the turning point, let's go back to our old friend, x is equal to negative b over 2 times a. Maybe it would help to rewrite this equation in standard form so that it's easier to identify our a and our b. So I'm going to write this as a of x is equal to negative x squared plus 1,000x, putting the x squared term before the x term. So going back to my vertex equation, the negative of b would be negative of 1,000 divided by 2 times the a, 2 times negative 1. So 1,000 divided by 2 is giving me 500. Now, because I know that I'm dealing with yards, I'm going to call that 500 yards. Because that's my x, that stands for the length of the field. We want the complete dimensions. So if we want the complete dimensions, that means I want to go back and find my width as well. So to find the width, we're going to say 1,000 minus x. So that's going to be 1,000 minus 500, which also gives me an answer of 500. Isn't that interesting? What we're finding then is that the field that makes a maximum area happens to turn out to be a square field this time. So think about that. We'll see some more examples of this in class. For exercise number 3, we're talking about the Crazy Caramel Corn Company. And they have figured out that the percentage of kernels, so they're making like popcorn, that pop rises and then falls as the temperature of the oil the kernels are cooked in increases. So our variables are going to be T for temperature, that's going to be my independent variable, and P for the percent of kernels that pop. Now obviously if the company wants to make the most money, they want as close to 100% of their kernels to pop as possible. So the equation that puts these two pieces together, as temperature increases, what is the change in the percent of kernels that pop, is given to us as P is equal to negative 101 over, sorry about that, let me start over. P equals negative 1 over 250 T squared plus 2.8 T minus 394. So the first question says, let's algebraically determine the temperature at which the highest percentage of kernels pop. So if I want the highest percentage of kernels, I want the maximum point on this parabola. So in order to find the maximum point on the parabola, let's go back to our equation for the vertex. This time our independent variable is t, so I'm going to start with t is equal to negative b over 2a. So we're going to say negative of 2.8 divided by 2 times the fraction negative 1 over 250. Now I entered this into my calculator by saying negative 2.8 divided by, and then make sure you put this whole thing inside parentheses as well as putting parentheses around the fraction in the denominator. When I did that, I found out that the answer for the temperature turned out to be 350. So that tells me that the maximum is going to occur, the maximum percentage of kernels are going to pop when the temperature of the oil is 350 degrees Fahrenheit. So keep in mind the situation that we're talking about here. Now determine the percent of kernels that pop at this temperature. That just means that I want to solve for the p-value at that particular temperature. So again, I'm going to show my work always, always, always on paper by showing that I am substituting 350 in for the t. But then you've got some options. You can type it in exactly the way I'm writing it, or you can store 350 on your calculator and go ahead and type in your equation. Now when I did that, I got that 96% of the kernels pop at that point. So our maximum value of this function is that at 350 degrees Fahrenheit, if the oil is at 350 degrees, that's a degree sign, then 96% of the kernels will pop. So we see that by this function, I can actually never get all the way to 100% of the kernels popping, because this was my maximum point. The most kernels that can pop is 96%. Now we'd like to sketch a curve showing this function p. So take a few minutes. I set up my axes so that along the horizontal axes I'm measuring temperature, the independent variable, and I'm going from 0 to 700 counting by hundreds. Along the vertical axes, we're measuring the percentage of kernels that are popping, and that's going to go from 0 to 100 because the top percentage would actually be 100. In our case, it's only 96. I counted by tens going up that axis. Now you can use your calculator, so I'm going to move on to my calculator screens and then I'm going to come back to this screen so that we can see what the graph is going to look like. So this is what my graph looks like. I've labeled the maximum point at 350, 96. Now what I'd like to do next is use the 0 command on my calculator to find the two temperatures at which the percentage is equal to 0. So you're going to see that I've done this on my graphing calculator by using the calculate screen. So I'm pressing on my calculator second and then the trace key, and I'm picking zeros. If you don't remember how to do the zeros on your calculator, please come and see me so that I can go over that with you. So here's what I entered on my graphing calculator. I've got that the function is entered in my y1. Be really careful to enter exactly the way the function is written. I did put parentheses around the fraction. And then I showed you what my window on my calculator looked like. And then I've got a sketch of what the graph looks like, but I'm going to put that sketch on the axes right in my notes as well. So go ahead and sketch that out on your axes. So here are the answers that I found on my graphing calculator. I found that the first zero on my calculator, which is going to be the one right here, is going to be that the temperature was equal to 195 degrees when the percentage was 0 for the first time. And then I came over to the second zero, the second place where my graph crossed the x-axis, and I saw that the second place that happened was going to be at a temperature of 504.9, so I rounded that to 505 degrees, and I said that again the percentage that's going to pop at that point is also going to be 0. Now you'll notice that on my calculator I actually went back and switched my window a little bit. I made the y minimum be -10 so that I would be able to see values below the x-axis when I was doing that second calculate zeros. For the last question, it says if a typical batch of popcorn consists of 800 kernels, how many does the Crazy Caramel Corn Company expect to pop at the optimal temperature? So remember that the optimal temperature was popping 96% of the kernels. So that's the maximum that I can do. So if we are having a batch of 800 kernels, if we take 96% of 800, in my calculator I'm going to enter that as 0.96 times 800, and that's going to give me an answer of 768. So that will be 768 kernels will pop at the temperature, that's the maximum temperature, 350 degrees. That's the temperature when the maximum number of kernels do pop. So we've done a lot of good work today, both algebraically and also on our graphing calculator, to finish up modeling with quadratic functions. That's a major focus in Algebra 2 Common Core. So that's why we've spent 2 lessons on this, and we're going to spend some more time in class on this. Have a great night, and we'll see you next time. Bye-bye.